Hi, this video will cover section 7.3, multivariable linear systems. In fact, it's going to be a 3-variable linear system. Our objectives will be to use back substitution to solve linear systems in row-echelon form, to use Gaussian elimination to solve systems of linear equations, and to solve non-square systems of linear equations. And then at the end, we will do an application of this 3-variable linear systems to model and solve a real-life problem. So first, I feel like this section is your warm-up for section 8.1, which will be the solving systems of equations with matrices. And one of the things that we use is row operations that will be used for us to construct an equivalent system of equations. So right here we actually have the same system, but you can see that the one on the bottom has been simplified so that we could do a back substitution, which we will do that. And so the way you go from one to the other is by doing those row operations. And so in chapter 8, which is about matrices, we call them row operations, and then here I'm not sure what this book will call them, but there will be operations done to the whole equation. So one equation is considered in matrices will be considered one row. So we have 3 equations now, and we have 3 variables. So in the previous section, we were dealing with 2 equations, 2 variables. So the solutions could be graphed, or the lack of solutions could be graphed on a 2 by 2 coordinate plane, the XY plane. And when we are speaking about XYZ, 3 variables, we will be talking about a 3D coordinate plane. So like I was saying, the second system is already reduced, so we refer to that row in its row echelon form, which means that it has a stair-step pattern leading with coefficients of 1. And you can see that here. So the x has a coefficient of 1, the y has a coefficient of 1, and the z has a coefficient of 1. So right there is in row echelon form. You can see that here there is no x, so we say it's 0x for the third equation, and then also 0y for the third equation. So not only do we have the ones in a step pattern, but we also have zeros below the ones. So yeah, that is actually pretty useful, because from there what we could do is use back substitution to solve the system of equations. And so that's what we're going to do in example 1. We already have our system in row echelon form, and so what we do, as you can see, we already have the solution for z equals to 2. So we're going to substitute that number into the next equation. So equation number 3 is already solved, and then equation number 2. So we're going to take that, and I'm going to write the equation first. So this is y plus 3z equals 5. And what I'm going to do again is going to substitute the variable z with the numerical value. So y plus 3 times 2 equals 5. And now I'm going to be solving for y. So y plus 6 is equal to 5. And then y will be equal to 5 minus 6, which will give us y is equal to -1. So right there we have our second solution. And remember, we have a 3 by 3 system, meaning 3 equations, 3 unknown variables. So we need one more. So at this point we know 2 of them. So now we can go back to the first equation, and we will be substituting the value of z and the value of y to solve for x. So again, I'm going to write the equation here first. X minus 2y plus 3z equals 9. And then we're going to substitute now. So instead of y, we're going to, sorry, that was a minus. So instead of y, we're going to use the number that we found here, -1. And then plus 3, instead of z, we're going to use the number that we had here already, 2, and then we're going to solve for x. So we have x plus 2 because of the double negative, then plus 6 is equal to 9. So this is x plus 8 is equal to 9. So then x will be 9 minus 8, which will be equal to 1. And that will be our third solution. So the way that we could write our solutions, individually, like one at a time, depending what WebAssign is wanting for you to do, or we could also write them in an ordered triple. So because we have 3 numerical values, we don't call it an ordered pair, we call it an ordered triple, and it does have to be in order, X, Y, Z, alphabetical order. So 1, -1, and 2. Now, we're going to talk about the Gaussian elimination, which will be the process that we will use to get to that row echelon form. So, and it's named after the mathematician who, I guess, created the steps or the method. So, we will talk more about him in the next chapter. So, like I was saying from the first example, we want to have equivalent systems, and to solve a system that is not in row echelon form. So first we convert the regular system into a row echelon system by using the following operations. So the operations that with matrices we call them row operations, so we're going to do the same for equations. So the things that we could do is interchange two equations, and the reason we say that is because we want to have the coefficients in that step pattern, like 1x, 1y, and then 1z. We want to have that, and then we want to have zeros below the ones. And so that's why sometimes the first equation might be already might just have y and z, and it might be in the first row, so maybe it will be more convenient to put it in the second row. So we could do that, and then we could, if not interchanging them, I am not a big fan of interchanging because, you're more likely to make a mistake when you interchange, but you're free to do so if it is convenient. Then another row operation is to multiply one of the equations by a non-zero constant. So kind of like with the system of the method of addition or elimination, we use non-zero constant, meaning they could be positive or negative, but not zero. And we do that so that we can cancel terms. So that is kind of like the idea here. And also the fact that we are allowed to add the multiple of one equation after we multiply an equation by a non-zero constant is considered to be the multiple of one equation. So we can add that new equation to another equation to replace the later equation. I know it sounds really weird, but once we do the example, it will make a little more sense. So rewriting a system of linear equations in row echelon form usually involves a chain of equivalent systems, which you can obtain by using one of the 3 basic row operations that we discussed on the previous slide. The process is called Gaussian elimination after the German mathematician Carl Friedrich Gauss, and he's one of my favorites because he did a lot of work not only with matrices but also with sequences, for example, and in fact, yeah, and we did mention this in chapter 3. There is an exponential function that or a group of exponential functions that are considered the Gaussian exponential functions. One of those is the standard normal distribution. So there's several things that he did, and he started making all of those formulas since he was a little kid, like in elementary. So example 3, we're going to use that system to solve, that method, Gaussian method, to solve the system. So you could look at the equations 1, 2, and 3, and you could see that for our first equation, we already have what we need, which is that 1 for the x. And one thing that you should always do when you solve a system is to reorder it so that it's always in alphabetical order. So first the x, then the y, and then the z. And even if you don't choose to do that, at least make sure that they do match by column or vertically, like that. You have all your x's, and then all your y's, and then all your z's, and then after the equal sign, you will have all of your constant terms. So that is a very important thing to do. And so then now, if we look at the system, we could see here on the solution that the leading coefficient of the first equation is already a 1. So we're going to keep that x in the upper left corner position because it already has that coefficient. So what we're going to do is write equation 1, and we're going to eliminate the x term from the first column. So you guys see how equation 2 luckily has a negative x. So if we write the first one, x minus 2y plus 3z equals 9, and then I'm going to write equation 2 right below, negative x plus 3y is equal to negative 4. And so here we're going to add, you can follow the steps here, add the two equations. And so you could see x minus x will be a 0, negative 2y plus 3y will be 1, positive y, and then 3z plus nothing, it will just be 3z. And so that new equation is actually going to be my new equation number 2, this part right here. So we're done with 1, we're done with 2, we reduced it so it doesn't have the x term, and now you can see clearly how the y has a coefficient of a 1. So here's our new system, the equivalent system, so it's just with the new equation number 2. Okay, so now we need to work with equation number 3 so that we can eliminate the x term, eliminate the y term, and then have this 5 turned into a number 1, because that is what we need to do. So we also want to make the coefficient of the z a 1, but we can't just do that, like using magic. So what we are going to do is we are going to take equation number 1, like it says here, and we're going to multiply it by negative 2. Why by negative 2? Well, if you notice, the x in equation number 3 has a coefficient of positive 2. So if we take this equation, the first one, and we multiply that 1x by negative 2, we will have negative 2x. And so once we add the two equations, we will be canceling or eliminating the x variable from equation number 3. So we're going to do that, and let's write it here. So negative 2, and if you notice, the coefficient or the non-zero constant that we're using happens to be the opposite of what we want to cancel. So opposite signs. So 2 multiplied to the first equation. So I'm going to write the first equation here. And it is very important that you multiply that all across the equation, including to the constant term. So I'm going to write my answer below. So negative 2 times x will give us negative 2x. Then negative 2 times negative 2y will give me positive 4y. Then negative 2 times 3z will give me negative 6z. And then negative 2 times 9 will give me negative 18. So now I'm going to follow the steps here. I'm going to write equation number 3. So that is 2x minus 5y plus 5z equals 17. So now we're going to combine like terms, or add the equations. So negative 2x plus 2x, that is 0, so we say it cancels. Then we have 4y minus 5y, and that will be negative 1. And then we have negative z plus 5z, so that will be negative z. And then for the constants, we have negative 18 plus 17, so that is negative 1. And so that is our new equation number 3. Or yeah, so you can see that new equation is already written down here on the next slide. And we're almost there. We already have in creating that step pattern, so we have 1x, 1y, and we need to eliminate the y from equation number 3 so that we have and also turn that negative z into positive z. So what makes sense for us to do is, if you notice here, we have positive y and negative y already. So it will be enough for us to just add those two equations together. So you know that, and I'm going to do that below here. So 1y minus y, that will cancel it out. And then we have 3z minus z, that will be positive 2z equals, and then 5 minus 1 will be 4. So it's very important that everything you do to the variables, whether it's you're adding vertically or multiplying by a constant, you also apply that to the constant term that is after the equal sign. So that's how we obtain the new equation number 3. And now, just to be done, the last thing we need to do, we already have a 1 here, right here, a 1 here. And what we want to do is turn that 2 into a 1. So it's pretty simple because what we're going to do is multiply that equation by the multiplicative inverse. And the multiplicative inverse is not the same as the opposite. Opposite is like opposite signs. Multiplicative inverse is that number that we multiply 2 by so that we can get a 1. And that number is going to be 1 over 2, like that. So you know that if we do that, when we multiply the fractions, we multiply straight across. So we will have 2 over 2, which is equal to 1. So that's why 2 and 1/2 are multiplicative inverses of each other. So what happened here is that they took that equation number, what is it, 3, 2z equals 4. And if you multiply by 1/2, it's the same thing as dividing by 2. And I think it's pretty obvious if you see this equation that all you have left to do is divide by 2 on both sides, left and right. However, I want you to get used to the idea of multiplying. If we go back to the row operations, you can see that we do not use the word division. And that is because we're going to translate this concept to matrices, and division is not defined for matrices. So if you see here for the row operations, we only have multiply and nothing, we have nothing that says divide. But remember, if you're multiplying by 1/2, you're actually dividing by 2. If you were multiplying by 1/3, you're dividing by 3. So, it's the same thing. Okay, so 1/2 times 2z, that's how we obtain the 1z. And then 1/2 times 4 is like you have 4/2, which is equal to 2, right? So that's what we have here for a constant term. Now, we have found one of the numerical values, z is equal to 2. And so what we have left to do to solve the system is to use the back substitution. So we're going to do that. So we have the first solution. In fact, that's equation number 3. I'm going to change that. 2 and 3. So I'm going to take equation number 2. I'm going to write it down first. So it's y plus 3z equals to 5. And I'm going to substitute the variable z with the numerical value 2. So that will be y plus 3 times 2 is equal to 5. So then y plus 6 is equal to 5. So then y is equal to 5 minus 6. So y is equal to -1. Now that we have a second numerical quantity, we could go back and take equation number 1, and it will be x minus 2y plus 3z equals 9. And now we're going to substitute the y and the z with those numbers. So here with a 2, and then here with a -1. So let's do that. So x minus 2, the y value is a -1. And then we have plus 3 times 2. And then we have equals 9. And so we have x plus 2 plus 6 equals 9. So combine like terms, and that will be x plus 8 equals 9. So then x is equal to 9 minus 8. So x is equal to 1. And we have our 3 solutions. If we need to enter it as an ordered triple, it will be x first, so 1, comma, then the y, and then the z, which is a 2. And that's it. Okay, so as with a system of linear equations in 2 variables, the solutions of a system of linear equations in more than 2 variables must fall into one of 3 categories. So just like we did with systems of 2 by 2, we had systems that had only one solution. We had systems that had infinitely many solutions, that were the ones where the lines were overlapping. That was infinitely many solutions. The one solution was just like 2 lines intersecting each other at one point. And then we had, for the ones with no solution, we had parallel lines, something like that. That was no solution. So now, how could we look at the that from the 3 by 3 system? And so the next slide has some pretty good images. So we're still going to have that 3 categories: one solution, infinitely many, or no solution. And so we have learned that the system of 2 linear equations and 2 variables can be represented as a pair of lines intersecting, as the one here. I'm going to fix that a little bit. It looks too ugly. Okay, so let's do 2 equations, different colors, so it makes a little more sense. Let's do that. So they're intersecting here. So we have the one, they intersect, the one that are coincident, and the parallel. Okay, so here it goes. This is how they look in a 3 by 3 system. So if we have when we are in the, we call it R. Remember the sign, the symbol for real numbers is an R, capital R with like a double leg here. That's the symbol for real numbers. So when we solve equations in a 2 by 2 xy plane, we say that we're working in R2. When we're working in 3 variables, we are working in R3 because we have XYZ. And imagine that in R2 you have lines, right? And so in R3 you don't have lines, and you have planes, not airplanes, but like a sheet of paper, or like your wall or the ceiling. And so that is what we have instead of lines. So you can see here, let's start with no solution. Well, okay. Yeah, let's start with no solution. So you can see here from the right, no solution. You have 3 planes. So this is representing equation 1, equation 2, equation 3, and they're like in different colors. And you can see that they are parallel. So just like parallel lines that don't intersect, the parallel planes do not intersect. So we say they have no solution. No solution. Simply because there's no intersection. Then the second one here from the right is also no solution, because you could see how for example, the blue and the yellow plane intersect here. Then we have the pink and the yellow plane intersecting here. And we also have, if you look on the back, the blue and pink planes intersecting here. So there are intersecting 2 at a time, but there is no point at all where they all 3 intersect. So this is also no solution. They're not parallel, but they simply don't, not all 3 intersect. So not all 3 intersect at the same time. Okay, now let's move to the one in the middle. And this one in the middle, what we have is similar to the 2 lines that are overlapping each other in the 2 by 2 system. But what we have here is the 3 planes overlapping each other. So in fact, you only see the yellow one, but the pink one is also overlapping here, and so is the one in blue. All 3 of them are overlapping, kind of like 3 sheets of paper together, stacked together. That's what it will be. And so if you think about it, they don't intersect only at one point or one line. They in fact intersect everywhere. Like every single point that is on the plane, every single point will be a solution. Every single one there. So it's going to be infinitely many solutions, and it will be the whole plane. So we will see an example like that, I think. And then for infinitely many solutions, actually this 2 are both infinitely many. However, where you have all 3 planes overlapping each other, you have any point on the plane will work. With the other example, you could see how they are intersecting. All 3 of them are intersecting at a line. So the solutions for this one are going to be all those points that are on the line of intersection. Not any point on the planes, but only the points that are on that intersection line. And so I don't want to say that like the ones on the plane have more solutions, because the concept is in reality infinitely many. You can't really say this infinite is bigger than the other. But yeah, just think about like so many. The difference is the way that we're gonna represent them. Okay, and then lastly, we have the one that has one solution only, and that is because all three planes, the yellow, the pink, and the blue, they overlap here at one single point. I'm trying to, right there, that is our solution. So that is just one point, and it will be like the systems that we've been solving, one order pair. Like for example, I don't know, I think we got like 1, -1, 2, or something like that. So that could be one solution. So to make you think a little bit about it, I want you to look around the room and pick up a corner of your room, and or wherever you are. If you're outside, you can't do that, but look at the ceiling, and then look at the two walls that are intersecting at a line. So two walls that are next to each other, intersecting at a 90-degree angle, and then you have your corner, which will be the ceiling, will be above them. And so the corner, that will be the solution if your walls were what we're talking about here, equations, and your ceiling was the other one. So that is a way to visualize it. Now, we've been talking about systems that have three equations and three unknown variables. And so you keep hearing me say 3 by 3. It's just like a habit. 3 variables. And so to get a numerical solution for 3 variables, you need to have at least 3 equations. So what happens if you have less equations than 3, and you have 3 unknown variables? Then you cannot solve the system fully and get numerical solutions for all 3 variables. But you could solve them in some way that one is written in terms of the other. So far, each system of linear equations you have looked at has been square. Square, we mean like the same number of equations, the same number of variables, like 2 by 2 or 3 by 3. And the example we're going to look next is called a non-square system. And so the number of equations differs from the number of variables. It could be more equations than unknown variables, or vice versa, less equations than the unknown variables. So just like a rectangle. And then square systems, like a 3 by 3. Imagine that's like a perfect square. So a non-square system and a system of linear equations cannot have a unique solution unless there are at least as many equations as there are variables in the system. So that's what I was talking about, having the same number of equations and unknown variables to be able to get a unique numerical solution. So if you don't have that, then you won't be able to get numbers. So you can see here we have two equations. So this is a non-square, it's a rectangular, as you can see. Two equations, and we have 3 unknown variables. And those unknown variables are x, y, and z. Okay, so what I can do here is take equation number 1. Okay, so what we're going to do instead, we are going to use the same Gaussian elimination. So what we're going to do is follow the steps that we did previously. So we want that x to have a 1 for the coefficient. Now what I'm going to do is look at what will be the opposite of 2. So talking about a number that I can add to 2 and get a 0. And so that will be the number with the opposite sign, which is -2. So I'm going to use the coefficient or the non-zero constant -2 to multiply the first equation because that's the one that already has the desired one that we need. So x minus 2y plus z equals 2. And then I'm going to write the step here. Multiply equation 1 by -2. Remember, because that's the opposite of the 2x. So we do that, -2x, and then -2 times -2y, so that will be positive 4y. And then -2 times z will be -2z. And then -2 times 2 will give me -4. Now I'm going to add, I'm going to rewrite here equation 2, which is positive 2x minus y minus z equals 1. That's equation 2. I'm going to add them now vertically. So -2x plus 2x cancels out, so that will be a 0. Then we have 4y minus y is equal to 3y, and then -2z minus z is -3z, and then -4 plus 1 is -3. So I mean, it's similar, but I just wanted to follow the step pattern. So now our two equations, I'm going to write them, the new system or equivalent system that we have created in echelon form is row-echelon form. It's going to be the first equation, which I'm going to write here, x minus 2y plus z equals 2. And the second equation is this new one here, 3y minus 3z equals -3. So now what I'm going to do is solve for x and y in terms of z. So what we do here with this equation is, and this is how it works. It's going to be a little weird at first. Z is going to be any number. So we just say z equals z. Then for equation number 2, I'm going to solve for y. So I'm actually going to need more room. And so if I take 3y minus 3z, and then I solve for y, I will get the following. So 3y is equal to positive 3z minus 3. That's the constant term. And then I have to divide by 3. So it will be y is equal to 3z minus 3 divided by 3. And remember, it divides both the term with the z and the constant term. So this will be y is equal to z minus 1, just like that. So then the value for y here, instead of putting a number, we're going to put the equation, or actually the expression, z minus 1, just like that. So the way this will work is like, if we feel like, okay, let's make z equal 1. then y will equal, we substitute the 1 into the y equation, and it will be 1 for z minus 1, so it will be 0. That's how it works. But if we say, okay, I feel like having z equal 10 right now, then if we substitute 10 here, the y will become 10 minus 1, which is 9. So those are possibilities, right? They're just examples. Now we have to do the same thing for the x. So we're going to take the equation that we have here for x, the first equation. So we have x minus 2y plus z equals 2. And I'm going to solve for x. So this is pretty easy because we have x here by itself already has a coefficient of 1. So we take the negative 2y across the equal sign, it will be positive. We take the positive z across the equal sign, it will be negative z, and then the plus 2 is still there. So let's just stick to the first example I gave you. So if I decide, well, first let me write the answer for x. It will be the expression 2y minus z plus 2. That will be the answer. So this right here is the answer. So if we say, okay, I want z to be 1, so then y is going to equal to 1 minus 1, which is 0. And then now that I have those two, if I want to find the value for x, it will be using this expression here. So it will be 2y minus z plus 2. So let's see what it will be with the constants that I chose here. So x will equal to 2 times 0 minus 1 plus 2. So this will give me x is equal to negative 1 plus 2, which is 1. And so that's how it will work. So I will make it part of it. X equals to 1. That's what I got. So that will be one example of a solution for a system like that that has two equations and three unknown variables. And the solution, actually, you might be asked to enter it this way on WebAssign as an ordered triple. It will be with the equations. So I'm going to write it up here, actually. So we say, so I'm going to use the equations that I have here. X for y and z, okay? So first for x, instead of a number, we have the expression 2y minus z plus 2, comma, then we have the one for y is z minus 1, and then finally the one z equals z, we just leave it like that. And if they ask us, okay, can you try to give us a solution set, then it will be something like what I found here. So where you assign a value for z and then you start back substituting. So a sample of that will be the order pair 1, 0, and 1. Okay, so that will be how you do it. And if you think about the geometrical representation of them, they are infinitely many solutions for that system. So we could be talking about a system that is intersecting at a line, and that's where all these points will come from that same line. Okay, so we're going to move on to our last problem, which is about vertical motion, and this is a very typical problem in physics. So it says the height at time t of an object that is moving in a vertical line with a constant acceleration a is given by the position equation. So here, position, and this is the same variables that you will use in physics. For position, we use the letter S. And then here, A is representing the constant acceleration. So for example, in our planet, I believe our constant is 9.8, but that is different in other planets. Now, there's a thing called air resistance, and actually, let me go back. That will be for a free fall motion, it will be gravity, and that's why I'm saying 9.8. It could be a little off. So for other planets, it will be a different constant for gravity, or for the constant acceleration. So there's another thing called air resistance, and air resistance is something that will completely change gravity. um I don't want to like get off topic right now because I'm trying to make this video short, so I will not get into that today, but I will send you the link of a video where you can see two objects with the same weight free falling with air resistance and without air resistance, and I think like it's gonna make a lot of sense. Anyways, going back to the problem. S is the position, and in this case, for vertical motion, we're using that position as the height, or it is representing the height in feet of the object that has been thrown. And I usually don't even care what the object is. Sometimes they tell you what it is. So A is the acceleration. We already know that. So S is the height in feet. A is the acceleration in feet per second. And then T, you already know, T is time, and in this case is in seconds. And then we have other constants. V sub 0, remember, is the velocity. The subscript indicates the velocity at time 0. So therefore, it's called the initial velocity. So this is V at t equals 0. That's why it's initial. And oh, it's actually here. And then S sub 0 is going to be the initial height. So it will be the position, or the height, or the vertical position at t equals 0 as well. So that's why we call it initial. Okay, so what we're going to do is find what those three are. So instead of finding like X, Y, and Z, we're going to be finding what, and let me see the way that we're going to write them. Okay, so we're going to follow the order. So we're going to be finding A, V sub 0, and S sub 0. And how are we going to do that? Well, we are going to use the data provided to us, and then we're going to create a system that will be a 3x3 system, and then we're going to solve them there. So the system, it's already written down here, but let me tell you where it comes from. So it says here that, oh, and again, here's what we're looking for. We're looking for A, we're looking for initial velocity, and we're looking for the initial position, in this case height. So we're going to use the data provided to us here. So it says that when S equals 52, that happens at t equals 1. So the height is 52 after 1 second, and that is this point right here. Okay, then we have that when S is 52 again, t equals 2. So you could see it here. And it's no surprise that that it looks like a upside down parabola. In fact, it is a quadratic equation. So then we have that S equals 20. The height is 20 at t equals 3, so at 3 seconds. So you could see this was an object that perhaps there was a person here, and this person threw the object here up in the air, and then it hit a maximum point, just like a parabola would, and then it came back down. And of course, that's not a very good trace, so let me do it with a highlighter. So the person threw the object up in the air. After 1 second, the height was 52. It hit a maximum height, which is the vertex, and then it came back down. And then at second 2, it hit the same height that it had at second 1, which was 52. And then it came back down. And then at second 3, the height was 20. So that is the free fall of the object. So we're going to construct a system here. So what we're going to do is use the equation that we had, the general model. Okay, so I wrote the same equation that we have here, here at the bottom, so that we can use it to create our systems. And so what I'm going to do is, instead of putting the S on the left side, I'm going to put it on the right side. So remember, S without a subscript is the output, like the Y value. And here the input is the T. So instead of X, we're using T for time. And the output is the position. So we copy this model here, and it says that we have 1/2, and then A, and then T. We're going to be substituting T with the number provided to us. In this case, is going to be a 1. So we're going to have plus V sub 0 times 1, and then plus S sub 0, and then the height, as you could see here, is 52. So we write 52 here. Then for our second equation, now we're going to substitute T with a 2. So here, oh, and I'm missing another one. So it's 1/2 A and then 1 square. We have to substitute it in both. So where the T square is and where the T is at. So here and here. That's what we are substituting. With the numbers that come from here. All right, so second equation, 1/2 A. Now T equals 2, so it's going to be a 2 square plus, instead of just, oh, here I'm missing B sub 0. Actually, I need to correct this. So please correct this on your notes. Plus B sub 0, and now instead of 1, I put a 2 plus S sub 0, and then the height, as you could see, is 52 as well. Okay, and we have here 2, 2. All right, now for our third equation, now what the number that we're going to substitute for T is a 3. So we have 1/2 A and then 3 square plus B sub 0 parentheses 3, and then plus S sub 0 equals, and I need to check what it was, is equal to 20 at T equals 3. So we put a 20 here. Now what I'm going to do is reduce or simplify the systems. So we're going to have that first here, 1 square is just a 1. So 1 times 1/2, it will just remain as 1/2. So 1/2 of A plus, we have V sub 0 times 1, so that will just be V sub 0. And then we will have plus S sub 0 equals to 52. Okay, our next equation is going to be 2 square is a 4. And then 4 times 1/2 is like 4 divided by 2, so it's going to be a 2. So 2a plus 2v sub 0, and then plus s sub 0 equals 52 as well. Okay, then the next equation is going to be, first we need to calculate the 3 squared. So 3 squared is 9. 9 times 1/2 will be 9 halves. We don't want to use decimals. We want to just leave them there as fractions. 9 halves times a plus 3 times v sub 0 plus s sub 0 equals 20. So right there we have our system. However, we're going to do something to help ourselves solve it and make our life easier. And so we're going to multiply the first equation by the constant 2. Why? Well, because I want to get rid of that fraction. So if you notice, 2 times 1/2 is a 1. And so that will be right here, you see, 1a. And that's what we always want, to have a coefficient of 1 on the upper left corner. So then we have to do it all across. So 2 times 1v sub 0 will be 2v sub 0. And then 2 times s sub 0 will be 2 times s sub 0. And then we also extend that to the constant term. So 2 times 52, we get 104. So that is how that equation was modified. So we have here our new equation 1. They are equivalent as long as you do that same operation to the whole equation, including the constant term. So for equation number 2, you can see that all the coefficients are already integers. So there's no problem. We don't have fractions, so we just leave it like that. Equation 2 is right there. 2a, 2v sub 0, 1s sub 0 equals 52. And then finally, for the third equation, we are going to also get rid of the fraction, the half. So again, the same trick, we multiply by 2. So 2 times 9 halves is equal to 9. So 9a, and then 2 times 3 v sub 0, so we get 6 v sub 0, and then 2 times s sub 0 will be 2 times s sub 0, and then 2 times 20 will be 40. So there we have our third equation. And from here, we could solve them by using the Gaussian elimination method. But I actually want to show you something else that I think it might be helpful and perhaps easier to some of you. So what I'm going to do is take 2 equations at a time. And I'm going to choose to take equation number, let's see, what could we do? Let's take equation number 2 and number 3. So equation number 2 says 2a plus 2v sub 0 plus s sub 0 is equal to 52. And then equation 3 is 9a plus 6v sub 0 plus 2s sub 0. And what I want to do is multiply one of them so that I can cancel one of the variables. And so I want to cancel s sub 0. So you can see that I have positive 2 s sub 0. And what I want to have is negative 2 s sub 0 and positive 2 s sub 0 so that I can cancel them out. That's my goal. So the way I'm going to get that done is by multiplying the equation number 2 by 2. So multiply equation 2 by 2. And so what I'm going to get from there is going to be 4a times 4 v sub 0 times 2 s sub 0. Oh, no, actually not 2. Sorry. I need more space here. So that was equation 2 and this is equation 3. I don't want to multiply by 2. I want to multiply by negative 2. So negative 2. That's what we need to do. So I'm going to start this again. So we're going to have negative 4a minus 4v sub 0 minus 2s sub 0 equals negative 104. Okay, that's my new equation 2. Equation 3, I'm just going to rewrite it here. And now what I'm going to do is add them together. So negative 4a plus 9a is 5a. Then we have negative 4v sub 0 plus 6v sub 0 is a 2, positive 2v sub 0. And then here we have the opposite coefficient, so we can cancel that variable, and then we add the numbers. So 40 minus 104 is negative 64. Okay, so there is a slight error that I made, and I'm trying to figure it out. So far I got to this part. I know that was correct. So I am going to check my next step. So I grabbed equation 1, and then I took equation 3, and then I distributed a negative 1. So let's see. And we're trying to cancel out the same. So negative, negative, negative. So we got negative here, cancel that, positive 64. Then we took equation 4, which is here. Then we took equation 5, which is here. And what we did after that, oh my gosh, I know what I did. I know exactly what I did. No, not really. Okay, let's see. So we wanted to have a positive 4 for v sub 0, so we decided to multiply by 2. So then we should have gotten 10a, and then 4, and then 2 times negative 64 is negative 128. Okay, then nothing changed to this, and we got 2a equals negative 64. So a is correct. I know that for sure. So let's see. The error could be here because we know that v sub 0 is not 0. So let's see. It must be somewhere here. So let's see if we get a better result. So 5 times negative 32 plus 2 v sub 0 equals negative 64. So let's see. 5 times 32. Oh, I see. What I did, I remember now. I multiplied that. Instead of a 5, I used a 2. And then I got negative 64. That was the problem. So it should be 5 times negative 32. So that will be negative 160 plus 2v sub 0 equals negative 64. Okay, now this should work out. So 2v sub 0 is equal to negative 64 plus 160, and that will give us, let's see, 96 positive, and then we divide by 2, and that will give me 96 divided by 2 will give me 48. Okay, so that should be the answer, not 0. And now I can go back here. A is negative 32. The initial velocity is 48. I don't think we have any units here. Seconds and feet. Okay. So what I was going to do was solve for the third one that we don't know. So not there. You can't even find it. So yeah, it was here. So I'm going to erase all of this. We don't need it. And we're going to use the fact that A is negative 32. And then we have, and the reason is, I know I mentioned 9.8. It should have been not negative 9.8, but that is the acceleration constant with metric system. So with using meters. Here where the units are feet, so that's why it's negative 32, but it's still the same. Then we found that initial velocity was 48, so I'm gonna need that. And then again, we're gonna use equation number 2. So this will be 2 times negative 32 for A, plus 2 times B sub 0, which is 48, and then plus S sub 0, and that will equal 52. So here we have negative 64 plus 96 plus S sub 0 equals 52. So I'm going to add the numbers here. 96 plus negative 64 is 32 plus S sub 0 equals 52. So then S sub 0 is going to be 52 minus 32, which we all know is going to turn out to be 20. So now we have everything. So the initial position was 20 feet up in the air. Yeah, you could see it. It kind of matches here. At time 0, that's the position, 20. And then the initial velocity, it was 48 feet per second. And then for the acceleration, we're going to have negative 32 feet per second square. And that will be the solution. I know this problem is long, and but I promise you, if you have to take physics, this is actually very helpful. So I apologize for making that mistake, but you know that things could happen. So again, I multiply by 2 instead of by 5. So, you know, don't do things like that. The way I recognized my mistake was because I was getting a really big number for the initial position. And if you see the graph, you could see here that it wasn't that big like I was going to get. All right, so this is the end of the video. Thank you for watching.